This is about diving deep into the semantic search using vectors. It's a short talk that we crumbled in a kind of last-minute setup. So here we are. So myself, Parth Pandit, I'm a senior solution architect with AWS. Came from the US, live in Dallas, Texas. And unfortunately, since this was last minute, as I said, my partner, Amar, could not join us. But he's virtually present here with his recording for his portion, and I'll take up from where he leaves his part. So with that...
Thanks, Parth. Hello, everyone. I couldn't make it in person today, unfortunately, but I'm excited to be presenting to you all. My name is Amar Yashlaha, and I am an analytics solutions architect at AWS based out of the New York area. Today's session will give you an understanding of some of the inner workings of OpenSearch vectors and how you can start using it to build Gen AI-based applications. Today's session is structured in 5 parts. I will go over how text search is different from semantic search. Then we will look at the role of vectors for semantic searches. We will also review algorithms available in OpenSearch and some of the parameters that you can use for tuning your semantic queries. Finally, we will look at an example, after which Parth will bring these concepts together and walk you through the design of how you could build a RAG application using OpenSearch as your vector store. On this slide, we have a short recording of a user looking for information about Wild West. On the left side, you see the results of a lexical search, also known as a text-based search. We see 3 very diverse results based on matching the word wild or west or both in the text of the image description of the data, resulting in a basketball game, a wild animal, and a pet dog. Perhaps not very useful for the user's ask. In the results on the right, however, you see images of rodeo and cowboys, which is more relevant to the user's request for Wild West. The video is scrolling a little quickly, but trust me when I say that none of these results have the word wild or west in the image descriptions. Now, this is possible using vector representations of the underlying data, which allows us to search by meaning rather than the actual words in the search query. So what exactly are vectors? Vectors are powerful numerical representations of words or sentences or images used in natural language processing. The process of converting data, could be text or images, etc., into their numerical representation is called vector embedding. This is performed using an embeddings model. The embeddings process can be an external model or an external process. You could also use OpenSearch's neural plugin to perform embeddings during the ingestion process. The dimensionality of a vector, as you see, is the length of the vector array. This dictates how complex the relationships between data points can be. When generating embeddings for the sentence that you just see on your screen, the model will consider not just the words in the sentence, but also the relationships and semantic meaning between them. Vector similarity is a key concept in performing semantic searches. Let's assume we've created vectors for the terms that you see on your screen. We can see 3 groups, also known as clusters, indicating terms that are closely related. These clusters are formed as the embedding model has learned the semantic relationships between these vectors. If a user were to ask for a recommendation for a book on financial management, it would recommend the book Think and Grow Rich because it has a shorter distance to the financial terms cluster than the Sapiens book. Takeaway is closer the vectors to each other, it means that they represent similar information or ideas. We also want to specify how many similar neighbors have been found, also referred to as K, hence the term K nearest neighbors. For example, the user search in the blue text and a setting of K is equal to 2 returns the books Guns, Germs, and Steel and Sapiens. If, however, the K value were 3, the Art of Happiness would also be returned. So next, let's try to understand how OpenSearch measures distance between vectors. OpenSearch supports multiple distance calculations, also known as spacetime. You can measure the angular distance using cosine similarity or linear distance using Euclidean distance. There is a link for the entire set of distance calculations supported by OpenSearch on this slide. The key takeaways for distance: the choice of your distance space affects how nearest neighbors are determined during searches. The best choice will depend upon your specific use case and the nature of your data. The space type is specified when creating an index. So the next step is to look at algorithms to get a high level of understanding of how OpenSearch navigates a multidimensional vector space. OpenSearch supports two algorithms: hierarchical navigable small world, or HNSW, and inverted file, or IVF. An understanding of these algorithms will be helpful for tuning our queries. Let's start looking at navigable small world. The core idea of this algorithm is to build a graph with edges containing index vectors that are close to each other. When searching a graph, we begin at a predefined entry point and then move to the vertex which is closest to our query vector. We repeat the search process of moving from vertex to vertex, identifying the nearest neighboring vertices. Eventually, we will find no vertices that are closer than our current vertex. This is the local minimum and acts as our stopping condition. Now, HNSW is an evolution of NSW, where the graphs are stacked in layers. The layers are arranged such that in the top layer, we have the longest links, and in the bottom layer, we have the shortest. During the search, we enter at the top layer, traverse the edges in the layer, just as we did for NSW, until we find the local minimum. At this point, we shift to the current vertex in a lower layer and repeat this process until we find the local minimum of our bottom layer, which is layer 0. Although HNSW produces incredible performance, we have a few parameters that we can use to tune memory usage and thus manage the related infrastructure costs. M is the maximum number of edges in a vector will get in a graph. The higher the number, the more the memory the graph will consume, but the better search approximation may be. EF search is another one. So when a node is visited, its neighbors are added to the queue to be visited in the future. Once this queue is empty, the traversal ends. EF search is the size of this queue, and a higher value will increase the search latency, but may provide better search results. EF construction is the queue size for when a node is to be inserted into the graph. Again, a higher value will increase index latency, but may provide better search approximation. The last one is encoder. This is an option to reduce the memory footprint of a vector index at the expense of search accuracy. You can learn more about encoders on the link on this slide, but the key takeaway is you can tune these parameters to refine your search. Let's also look at the other algorithm. The IVF algorithm separates your index vectors into a set of buckets. Then, to reduce the search time, it only searches through a subset of these buckets. Now, before the indexing begins, it assigns each bucket a representative vector. When a vector is indexed, it gets added to the bucket that has the closest representative vector. However, because of this initial setup of buckets, in order to create an index that uses IVF, you will need to train a model using the train API before ingesting data into your OpenSearch index. And when performing a search, we start by looking at the centroids of the buckets. We find the closest centroid to the query vector, and then we explore that local area to find the k nearest neighbors. There are a few parameters that you can use to tune IVF. Nlist is the number of buckets to create. Higher value of nlist will result in longer training times, but may improve the granularity of the result. Nprobes is the number of buckets to search. Again, a higher value will mean a longer search time, but better approximation. Encoder is similar. You'd use this parameter to reduce memory consumption when search accuracy is a little less important. An engine is the library that implements the algorithms that we just went over. OpenSearch supports two engines, Lucene and Facebook AI Similarity Search, also known as FACE. Lucene is the native search library, and it only offers the HNSW algorithm. FACE is a library that implements both HNSW and IVF. This slide on your screen provides a comparison which can be helpful when you're trying to decide the engine and the algorithm for your vector search applications. But in general, select FACE for large-scale use cases with options to reduce memory footprint using encoders. Lucene is a good option for smaller deployments and offers benefits like smart filtering. So now that we've gone over some of the vector theory, the engines, and the algorithms, let's see an example of how you will create a vector index in OpenSearch. Creating vector index requires the following steps as part of the create index statement. So we'd start with a put command to create an index. We set the index.knn value to true to enable knn search functionality. We will specify a field that we will use as the vector field. In this case, it's my vector1. We specify the type for this field, letting OpenSearch know that this is a vector field. We specify the number of dimensions. In this case, we're using an embedding model that generates vectors with 5 dimensions. We also can specify the distance metric. If not specified, it'll use the default. In this example, we're using L2. We provide the algorithm information as part of the method keyword. In this case, we're using HNSW. And then finally, we specify the parameters that we want to use. These are set as default. These can be overridden with different values as needed. Now, once the vector index is created, you can ingest data into your index. To query the index, then we can use the underscore search statement. I'm going to show you a basic example. We need to provide the query type to let OpenSearch know that it is a KNN query. We need to specify which field we want to search against. We provide the vector representation of your user request for which we want to return similar results. And we additionally also specify the K value for the number of results that need to be specified. There are additional options, but this is a simple example. To quickly recap, we've discussed some of the theory around vectors, some of the tuning options, and we've looked at an example of how to create an index and then how to query it once it has been created in OpenSearch. Thank you all for listening. With this, I will hand it over to Parth, who is going to discuss RAG application design with you.
All right, so this was like how you can perform semantic search using vectors. So let me take a quick check here. Has anyone implemented a RAG application or working on a RAG application use case so far? 1, 2, 3, 4, 5. Yeah, good number. So what is RAG? RAG is retrieval augmented generation. It's a good technique to equip your large language model for the knowledge that it was not trained on. Now, we know that the training ends at a particular time for any model that you take, and anything happens after the training, model doesn't know about that. Or your proprietary data about your policies for your companies and all, model doesn't have any idea about it. So how to generate content based on that? That's the whole idea of retrieval augmented generation. And semantic search plays a very crucial role in making RAG working. So how it works? So it has basically 3 stages here, as you can see. The first one is data ingestion, where you specify your data source, where your documents are there, which you want to use for ingestion. And then divide those documents into smaller parts. And those smaller parts, we call it chunks. Now, for those chunks, you can feed them into a specific language model which knows how to convert those chunks into numbers. Because after all, it's a semantic search, which is number-to-number comparison to find the meaning about the search rather than the text. And then finally, as Amar showed, you can ingest those vectors into OpenSearch using the choice of algorithm, choice of engine, and other configuration. Now, in the retrieval phase, what happens is your user query has to be converted into, again, numbers, because then only the query will be searched against those vectors which we have ingested into OpenSearch. So again, user query is converted into vectors, but here the embedding model has to be the same, because then only you will have the similar kind of search result coming out. And then those search results will be acting as the context that you can provide to your large language model. And in the response generation, that context is added as a part of your prompt, and large language model generates the response. So let's take a step-by-step approach for all these three stages very quickly. So in data ingestion, your data could be several types of documents: XML, Markdown, Word document, CSV, images, PDFs, whatnot. So all those documents, you supply them in a data source, and then you chunk them. Now, chunking is another deep topic where there are multiple different strategies you can take. If it's a CSV file, your chunk could be one row of that file. If it's a PDF file, your chunking could be either a paragraph or a page, or even the title-wise chunking, depending on how granularly you want to create metrics. But remember, for every chunk, there is one metric created. More chunks, better search, but more compute will be required for your search. And then, for embedding models, there are various choices on Amazon Bedrock as well for embedding models like Titan and others. Or there are several third-party models for embedding that you can use to create the embeddings for your chunks. And finally, ingest them in OpenSearch. Now, again, in retrieval, the same process happens where a user query is taken out. There is a language model that you can use to generate the search payload for OpenSearch. And then that goes to the embedding model to convert that search text into the vector. And your search result is then derived as the context. Now, here the search results would be those K value that Amar was referring, K3, K4, K10, how many search results that you want to embed into the context. And all those search results then get into the prompt. Now, in prompt, there are basically three portions if you worked with prompt engineering a bit. One is system prompt, other is context, and third one is the actual request that goes from the user. In the system prompt, you say that this is my context, use it for content generation. LLM honors that, and finally creates the response for it. So that's all. In 20 minutes, we wanted to cover. But if you have more questions to learn about it, I'm here, as this is a break, and we can talk more about this topic. Yeah, thank you.
Thank you.
Yes.
Thank you for. I know there was a rush, but sorry, we started a bit.
Yeah,
late.
no problem. Yeah, as far as
there is already the break time, but because there is break time, we can extend it and go for some questions if you are interested. So I already saw a hand. Stavros, yes? Yeah.
But anyone who's desperate to leave should leave, since it's time. So I'm Stavros. I'm the product manager for search in OpenSearch. Great presentation. I love the introduction. The one thing that even in an introductory presentation should, I think, be mentioned is that in almost every case, hybrid search works better than vector search alone. And RAG, so as I like to say, garbage in, generated garbage out. So if your retrieval step is not ideal, your results will still be bad, even through RAG. I mean, RAG improves them, but it can't fix something that's absent. That's all. Just wanted to make a
No,
comment.
that's absolutely right. Hybrid search is the actual production use case. In production, you will have to go with hybrid search. That will also increases your search result. At the same time, it decreases the duration for the search because you filter out a lot of unwanted data for searching.
Hybrid search, so there are two definitions of hybrid search. Some of the VectorDB companies call hybrid search filtered vector search. I'm not talking about filtered vector search. I'm talking about hybrid search where you do a lexical search using BM25 and combine those results with semantic search using vectors. Filtered search is a different case, which I think the VectorDB vendors are being dishonest by calling that hybrid search. But I'm talking about the hybrid of BM25 or lexical search and semantic, which in almost every case outperforms either lexical alone or semantic alone.
Yeah, that's a good use case. I have not seen that, but I think it makes sense to first perform semantic search and then perform on top of it lexical search to even refine.
Two separate searches.
And then combine. Okay, good to know that.
More questions? Yeah.
All right then, thank you.
Thank you.